All right, so in this section, we're going to look at a couple applications of the intermediate value theorem and the other theorem we proved about boundedness and maxima and minima, but especially the intermediate value theorem. So before I look at those examples, these are like examples 1 and 2 in the book, I guess. But before we do that, I actually want to give a question here, a lecture question. So about what we've done so far. I guess this is lecture 12, question 1. So theorems 18.1, this is the maximum and minimum, and 18.2, this is the intermediate value theorem, tell us that if f is continuous and a, b, the closed interval is a subset of f, is a subset of the domain of f, then f applied to AB is a closed interval, right? This is because, so the intermediate value theorem tells us that f applied to AB is, the image of AB is going to be an interval of some sort, right? And then theorem 18.1 about maxima and minima tells us that it specifically has to be a closed interval, okay? So the question is, if AB in general, right? So forget about this situation, forget that the closed interval is a subset of the domain. In a general situation, if an open interval is in the domain of f, must f applied to the open interval be an open interval. Okay, so, as usual, take a little bit to think about it, write down your answer, make sure to include it with your homework, and when you unpause the video, I will go through the answer. Okay, so the answer here is actually no. So a simple example would be, sine of the interval 0, 1, or not 0, 1, sorry, 0 to pi, I guess, is the closed interval -1 to 1, right? And in general, well, actually, you do open things like this. If the function kind of goes up above and below the endpoint, delimiting it like endpoint values for, oh, well, okay. I guess I should have said we should assume f is bounded. Although actually, I guess that doesn't really affect it because infinite intervals where one of the endpoints, one or both of the endpoints are infinite, are also considered open. So it doesn't matter. All right. Anyway, yeah. But if in the bounded case, at least, if it looks like this, right, then it'll achieve these maxima and minima values outside of these two endpoint values, and so you'll end up with a closed interval that way. Okay. All right, so that's a simple enough question. So let's move on and look at these examples. So this is example 1, fixed points. Okay, so okay, let f be a continuous function mapping the closed interval 0, 1 to the closed interval 0, 1. So the domain of f is the closed interval from 0 to 1, and the outputs of f all fall within the closed interval from 0 to 1, okay? It doesn't necessarily hit all these values, of course, because we haven't said anything about f being onto or surjective or whatever, but all of the values of f have to be in this interval, okay? Then f has at least one fixed point, i.e. there exists x naught in 0, 1 such that f of x naught equals x naught, okay? So graphically, and I actually encourage you to think about this yourself before, looking. I mean, maybe you already read the textbook, but if you haven't, give yourself a chance to actually think about this, because it could be, healthy. How could you use the intermediate value theorem to prove this, basically? But the picture here is basically this. So we have, here's, 0, 1. Let's say this is 1. So basically the graph of f is in this box, right? And for f of x, for some x naught, for f of x naught to equal x naught means that the graph of f hits this diagonal line, right? Like that. So obviously, if f of 0 equals 0, then that counts already. Or if f of 1 equals 1, that also counts as a fixed point. So if we imagine that f of 0 is not 0 and f of 1 is not 1, right, then it has to be somewhere down here, and f of 0 has to be somewhere up here. Then the graph the graph of f has to cross this diagonal line somewhere, and the reason for that ultimately boils down to the intermediate value theorem. So there's sort of a trick, to make this argument rigorous. The trick is this. So define g of x equals f of x minus x for x in 0, 1. Okay. We wish to show g of x naught equals 0 for some x naught, right? Note that if, well, so, okay, I guess maybe what I should say is this. So suppose g of 0 is not equal to 0 and g of 1 is not equal to 0, right? Then g of 0 is greater than 0, right? Because g of 0 equals f of 0, and of course f of 0 has to be greater than or equal to 0. So if g of 0 is not equal to 0, then g of 0 is greater than 0, okay? Then g of 0 is greater than 0, and g of 1 is less than 0. Because if g of 1 is not equal to 0, g of 1 equals f of 1 minus 1. So f of 1 is less than or equal to 1. So the biggest this could be is 0. So if g of 1 is not equal to 0, then it has to be less than 0. So then the intermediate value theorem says there exists an x naught in the open interval 0, 1 such that g of x naught equals 0. Because 0 is then in between g of 0 and g of 1, right? And that's exactly what we wanted to show. So it's kind of a cute little, very cute little argument. And there are other, like, I think there might be a problem on the homework that uses kind of a similar trick for a different application. So this kind of idea comes back. If you can sort of take you're trying to show that some like algebraic condition holds, a lot of the time you can turn it into a question about the intermediate value theorem by just manipulating whatever equation you're trying to prove, I guess, has to hold for some value of x or something. Okay, so let's look at one more here, one more example. This is a bit different. this is about mth roots for m in n. Okay, so let y be greater than 0, then there exists some x greater than 0 such that x to the m equals y. Okay, that's what we're trying to show. We're trying to show that nth roots exist. So for positive integers m. Okay, we've kind of been taking that for granted up until now, but now we can actually show it rigorously using the intermediate value theorem. So when we put it this way, it becomes kind of obvious that the question f, or the function f that we want to consider to apply the intermediate value theorem to should be f of x equals x to the m. So consider f of x equals x to the m. This is continuous for all x, actually, by 17.4, I guess, 2, I think. I don't know. What do they say? Oh, they leave it as an exercise. Well, whatever. Anyway, yeah, so this is continuous, obviously. And so if we want to show that this happens, all we have to do is show that f achieves some value less than y and some value bigger than y. And so f of 0 equals 0, which is less than y. So we want to show there exists some value of f bigger than y. To see this, or like bigger, I guess it's enough to say greater than or equal to. Well, I don't know. I'll deviate from the book a little bit here. If y is less than 1, take b equals 1, then f of b equals 1, which is greater than y, right? If y is greater than or equal to 1, take b equals y to the m plus, or sorry, let's say y plus 1 to the m, I don't know, then f of, b, I guess take b equals y plus 1. I don't know, whatever. Then f of b equals y plus 1 to the m, which is clearly greater than y to the m, which is greater than y, since y is greater than or equal to 1, right? Well, greater than or equal to, I guess, in this case, but it's strictly greater than here. So, so y lies between two values of f. So the intermediate value theorem tells us that there exists an x such that, an x greater than 0. I mean, it kind of clearly has to be greater than 0. Well, okay, at least it can't equal 0. But because our left endpoint here is 0 and then b is greater than 0, the intermediate value theorem says we can find something in between 0 and b, right? So that's why x has to be greater than 0, such that f of x equals y. So that's that one. That's how you can use the intermediate value theorem to show that nth roots exist for positive integer m. So that's all for this part. And in the next couple parts, we'll be looking at, conditions of one-to-one, so injectivity for continuous functions, and also like monotonicity for continuous functions, because they're kind of related to each other. Okay.